So let me see if I can start this in the right spot. Oop, I grabbed the wrong slide even, just to make life more fun for everybody. It would help if I grabbed the one from the right book. So, this is that 7-layer, so it's like 7-layer dip, only we have a lot of different pieces to it. It's how we communicate. You may have been watching something like CSI or NCIS or any one of 100 different shows, and you heard the term TCP stack, or they said, ooh, the network stack, and the firewall, and all these things. This is where this actually comes from, and where they actually got some of their information. A lot of it's not accurate, but what it really looks at is this is an example. This is not with the names that we're going to use, but it's an example of how your browser works its way from the browser, which sits above your operating system, to the operating system, down to the hardware to send that signal out over a cable, and then at the server side, where it's going to look at that page, goes up to the hardware, into the operating system, and finally to that web server. So that conceptual model is what we're going to look at. That idea that we're going to send things up and down a stack. So we have all the way at the bottom. What's our programmers do not throw sausage pizza away? What does that P stand for? Physical layer. That's where we actually are going to send a signal in a wire, send a signal down a fiber, or send it out wirelessly. All the way at the other end is where our software is going to land. So that OSI model, programmers do not throw sausage pizza away. Now, we're going to find out it really should be called an 8-layer stack, and they really should have split one here in a little bit. But this is probably the hardest thing we're going to do all year, is work on modeling this. This is how all of our communications, when you pick up a phone, when you get on a web call, when you send an email, when you get on the internet, everything we do is really based around this OSI model. So here's an example that I think makes it a little more clear. It starts looking at where some of these things land. So physical layer, that hardware, that physical piece. But notice that data link layer also includes some of that. We have a network layer. We have a session, a presentation, and an application layer. And notice some of those names up there should start looking familiar already. Because we've talked about IP, right? And so notice TCP is up on layer 4, IP is on layer 3. Interesting. So our languages, that protocols, start looking at different pieces. All the way at the top, you see applications. So you might see things like email, a web browser, Microsoft Word. Any of those kinds of things are applications. So we can break it this way. We can say hardware, operating system, and then applications. And inside of that operating system is a lot of things that get built in directly. So there's a lot of pieces that we actually see. And we're going to look at some of those tools so we can see how they work. But things like HTTP, in other words, how we communicate with a web page. SMTP, you should have seen that one already. Simple Mail Transport Protocol. POP, Post Office Protocol. FTP, File Transfer Protocol. And I know some of you just got out of web design, right? I see some heads going, oh yeah. You guys are going to use FTP in there. So this is how we break up all that communications. So I prefer to really do it from the bottom up. The book likes to talk about it from the top down. So the book has more resources, so we're going to go with this. So it follows what you're going to read in the book. So when you read in the book, that application layer. So at the very top, when I see something like Google, and if you go to Google's page, you can see, hey, they have an API stack, an application interface stack. So application then says this is where we now interact with that computer. It is how we get data then back into it. So whether it's you typing, whether it's connection to a thermostat, that's always in this application layer. So payload then, or what we're going to send out, and down that stack is data that, so maybe it's what we've typed in, maybe it's a request to load our website. Whatever that happens to be, that's data that we're going to then go downwards with. Does that make sense? It's going to go down to the next layer. So what it goes down to then is that presentation layer. And the presentation layer, is responsible for formatting, or the one I really think I want you to remember when you have to write these out, is I want you to remember what encryption is. Does anybody think encryption is important now? Yeah. So session layer, or the presentation layer, sorry, is what deals with, in some cases, the encryption. So all of our data up to this point hasn't been encrypted. This way, we could start scrambling up that data so it is secure. Below that is the session layer. So the session layer connects between your computer and a different machine and keeps that session alive, if you want to think about it that way. So that session layer says, how are we going to send data? In what size chunks? What happens if we don't get that piece of data recovered or sent? So it is the one that maintains a session between your computer and another computer. It's kind of the shortcut way to think about that. So those top three ones, application, presentation, and session, a lot of their stuff is really very similar and entwined together. So there are times, and different models have said, these should really all be one model. But a lot of times we do break it out, and it depends on what we're doing. Does it make sense to break that into three pieces or keep it as one? So remember that. Some of these session, application, and presentation pieces look very similar. And part of that is, depending on the operating system, do we consider some of those programs as built in, or are they sitting on the top of that? So this is not without some controversy, and there are some 3- and 4-layer models that have said, hey, we should really replace this OSI model. What's really weird about this model is normally you build a model and then build a product. So if you're going to build a car, you build a model car and then you build the full-size car. We actually had the internet in some form back in the early 70s. We didn't develop this OSI model until the 80s. So it's a little backwards. But as we work our way down, we end up at something called the transport layer. And for us, what this does is it tells it how we are going to send payloads of data. And we actually have 2 different ways that we can send data. We can send that TCP, and you've already seen that TCP, Transmission Control Protocol. So, Transmission Control Language. Or you can send it with what's called UDP. And UDP sounds like something, if you get it, you need to go to the doctor, right? But it's not. There are 2 basic methods that we're going to send. So, Transmission Control Protocol is what we call connection-orientated. What that actually says is every time I send something out, I have to get an acknowledgement back from you that you received that package. So let me give you an example of transmission control protocol in action. Who do I have as a victim over here? Velma, I'm going to pick on you because you're right there. So Velma, we're TCP now. So everything I say to you, you have to say acknowledged when you get it, after you've heard the whole message. We're going to have some homework today. Say the word acknowledged. We're going to change the homework and not have any acknowledged. And so everything I say, you have to acknowledge it. If I don't hear her say acknowledged it, I just keep repeating it until finally that message gets through. So there's an advantage. I know that you got that message with TCP. So if I'm sending out your grades, for example, maybe I'm putting grades into Blackboard, would you like me to use TCP so that the grades actually get acknowledged that you get a grade? The opposite one of that, or a different one, is called that user datagram. The datagram says, I'm just going to send out all this information. I don't care whether it gets received or not. Now, we hope it all does get there, but a good example of that is this class. If I, in the middle of this talk, told you to do a certain homework assignment, about half of you would actually do it, right? The other half would go, I didn't hear you, because I'm too busy surfing on the web or playing on Facebook or whatever it is, right? So UDP sends it out, but there's no guarantee that you actually got it. So there's advantages, though, to each of them. With TCP, I know that information got there, but to do that, does it slow down? If I had to ask everybody in here, did you guys get my message, and you had to raise your hand, it would slow down how we could disseminate information. So picture streaming audio. So we're sending a lot of data out there. If you miss one little piece of data on that audio, are you even going to notice it? Probably not. But if I'm sending out all the bank information, are you going to notice it if your bank account disappears? Yeah. So it's what we use, which one we use, that becomes the appropriate message. So protocols, and we're going to go through some of this, the language, each area of this stack, those protocols add information at the beginning of that stream of data. If we completely encapsulate it, so encapsulate means we put things at the beginning and the end, or we wrap it around. So that means we're going to wrap data and we're going to put information at the beginning and the end of it. The transport layer, so each time it adds information, it adds things that are important to it. So the transport layer sends what's called a port number. So in your computer, we know we're going to get an IP address at some point. I'll show you what that is. But each computer also has what's called a port. So it's like individual mailboxes on your computer. Well, they're addressed in binary, and there's 65,536 different ports. You have to memorize every one of them. Most of them are pretty common that we use. So web traffic, for example, is always on, or almost always on, port 80. And so we know that port, if something gets to your computer and it's on port 80, we know that's where it's addressed to. So for right now, remember that this can be either TCP or UDP, and it adds a port number to that data traffic. So whatever our payload is, if it's a note, if it's a message, if it's a piece of music, all of that has to be added to so we know what it is. The reality is, remember, is our computer smart or dumb? They're dumb. All they can send is zeros and ones. I have to be able to tell what those zeros and ones are, right? So that's what we're doing now, is we're adding information at the beginning that says, hey, this is a piece of music. How is it going to get there? if that message is too large, because we're going to break it down into chunks that we can send, or packets, you're going to find out. If we need to break it down, if it's in TCP, it's called segments. If it's UDP, it's called a datagram. We break them down into chunks. That is the beauty of this whole thing, is we break data down into small enough pieces to send it as individual pieces. So we've got a lot of terms in here, and this is, quite frankly, a little bit messy. As we send it further down, so now we send it down to the network layer. So the network layer, hey, it's responsible for part of the network. So if you can think about that, once we get to the network layer, we're adding more information to each end of it, but now we're calling it a packet. So each layer has its own little name, and we're making it a packet. And so you'll see the term packet-based technologies a lot. What that really means is we break all this data down into small enough pieces, we call them packets, and we can send them around the world. So, if that packet, as it gets to this layer, needs to be broken down, we call that fragmentation. We break it into smaller fragments, so it's still that data, but we've had to slice it up. So think about a song. A song that you're going to get from, who's the latest artist out there? Youngboy. If we're going to get a new song from Youngboy, we're going to have to chop all those zeros and ones down that make up that song into small enough pieces that we can send it. So, we're going to look at, this layer also is where we start this idea called routing. In other words, we have a place that it's going to go, and we have some direction about how it's going to get there. In other words, we're going to route that package. So what we've done is, just like we went to the post office and we've put a city, state, and zip code now, and we know we can send those pieces out. Layer 2 then, that data link layer, is one of two layers that's responsible for interfacing with that physical world. So always before, we're in that electronic world inside of our own computer. Now we've got to get it out of our computer. So we have a lot of different ways we can get it out. We can send it on a physical wire like in here. We can send it on a wireless connection. We can send it on a fiber optic. So that hardware, this is how we start to make that determination, how it gets out of our computer. And so now we again have more information on it. We have a link layer header, and we call it something new. We call it frames. So there's a lot of terms in here. That's why I said this gets kind of a little bit ugly. In this layer, we also have something called a media access control address, or a MAC address. Has nothing to do with Macintosh computers. It's called a MAC address. Every device that's connected onto that network has a MAC address. They are hard-coded into this device. So, if I look on the bottom of this guy right here, and if I can see it in here, there is something called a MAC address. I'll pass this around. You can find it on every device. Your phone has a MAC address. Every computer and internet connection has a MAC address. It's burned into that device. And that MAC address tells us who made it and a serial number. They're all unique. Every MAC address is different. So now we have an additional address we can put in there. And then finally we hit that physical layer. So when we have that physical layer, I don't know where my fiber went to in my transceiver that was there, but that transceiver is that physical piece, puts it onto a copper wire, or puts it onto an optical, or puts it into a wavelength in the air. So this is kind of the simplest one, the physical. Says we've got all this information, we wrapped it up, And it's all wrapped up like a big giant package. And now we send it out over some connection. It arrives at its destination, and it goes exactly the same thing, but now we're doing it backwards. So now, it comes into your computer on the physical layer. It moves up to the data link layer. It moves up to the network, the transport, the session, the presentation, and the application layer until finally you get that message back. So data goes up and down this stack, up and down that stack over and over and over again. So here is a chart to kind of tell us a little bit about what's going on here in these different things. So we start out here at these first three layers. We know they're kind of tied together. And that's our payload, whatever it is. So that's your Word document you're emailing. That's a song from Young Guy, right? No, Young Blood. Young Boy. I'll get it. So that's the payload. As it moves down, it becomes a segment or a datagram, which is then wrapped into a packet, which is then broken into a frame. And then down here, it gets spent into a transmission out, whether it's out on a radio wave or whether it's however we manage to get it out there. So we have a lot of pieces about that. So this diagram might make more sense in some ways. So up at the very top, let's kind of follow this through. So you guys have this one available to you. You can go find it. It says, here's my browser. And that browser sits on top of that application layer. And it originally says, hey, I need to go get a new album from, we're going to pick a new album. Young Boy. We'll use Young Boy again. We're going to go get it. And notice here, in this middle, it starts to show you that header and that trailer. So the original payload says, get this album. Each layer adds additional data to it. Do you see that? So the first, there at the session layer, we add a header. And then we add another header, and then another header, and finally we frame it. And that frame makes sense to call it that because we put it on the front and the back. We've completely encapsulated that data. That data then leaves our computer, it goes over to the data link layer, and it goes, and it hits a router. And so a lot of times you will say a router is a level 3 device. Well, notice here it goes up 1, 2, 3, and back down 3. So anything that just does that, so all it has to do is get up to the network layer to see that routing information and comes back down. And every time it hits a router, it does that. Layer 2 switch just has to do the physical link into that data link layer. And then finally we get down all the way here, back up to our web server, and it's got to go all the way up to the top, open up that file, and now it's going to send that file, and it's going to follow that same path back. So our data gets manipulated a lot. When it reaches this, it starts stripping off headers, trailer, and finally it's left with just that original payload. It does it so quick, you don't realize that that's what's happening, but we send literally thousands and thousands and thousands of those frames every minute on your computer. So this is really how all those pieces work. This is probably the easiest way to explain a very complicated piece. If you can understand how we start adding those headers and trailers in, so we're just wrapping up that data. We're putting in pieces in front of it. So this is stuff we're going to come back to over and over and over again. So if I'm going to send that album to you, and I'm going to stream it, so you're just listening to it, that's where we might do the UDP. If I'm going to buy that album and I have it on my computer, do I want the whole album? Yeah, I don't want pieces missing. I would use TCP. In other words, every piece of connection I get. And so if it sends a packet all the way through there and it's damaged or it's destroyed or it's missing, it's going to resend it. And that's the beauty of TCP. TCP is designed to be resilient. In other words, if there's an error, we get additional data very quickly back. This original network was designed so that we could connect military bases in the event of a nuclear war. So it is designed originally not for sending music or movies or Netflix. It was really designed to send control and communications in the event of a nuclear war. Have we moved hopefully past that event? Depends on how you look at Russia right now and some of the events they're doing. This flip side of that is then that same resiliency benefits us. So if I'm trying to send data and all of a sudden Kansas City has a massive power outage, all those things will reroute and we won't lose any of that data that we're trying to send. So this OSI model is complicated, elegant, and has worked really, really, really well. This is probably the best way to think about those headers and those trailers. What is interesting, remember that computer just knows zeros and ones. So how does it tell where the header and the trailer is? So it's just a string of zeros and ones, right? That's all your computer gets out of that internet card is a string of zeros and ones. So if we didn't have that common languages, and we knew that, and I'm just going to make these up because these are not exact, I'm just trying to show you a short example. So if I knew that you're getting data, if we had a common language and it said, well, the first 8 bits, so a bit is 10 or 11, those first 8 bits are a header, and that says how long my packet is. This says you're going to get data, and it's going to be 1, 2, 3, 4, 5, 6 bits long, right? We have to agree on those common standards. Otherwise, all you're seeing is zeros and ones. And zeros and ones all by themselves don't make a lot of sense. So I want to look at a couple of things with zeros and ones. So we're all familiar with it. Can everybody multiply by 2? Everybody can multiply by 2? That's good. You guys have this down then. So everything our computer gets is zeros and ones. So we want a couple of terms just so we're not confused. And if I say something, you can go, I think I've heard that before, and maybe I haven't. So the first term that we want to make sure everybody knows is bit. A bit is either a 0 or a 1. It's the smallest unit of data we can work with. 1, 0 or 1, 1. That really doesn't tell us a whole lot. It says on or off, right? Well, we logically started connecting them together. And the next unit of data we're going to have is called a byte. B-Y-T-E, a byte. So you have bits and you have bytes. This unit, we said, well, we can make a useful sized chunk of data with stacking some of those bits together. And what we actually did was we put 8 of them together. So a byte is 8 bits. 8 zeros or 8 ones. All right, here's where those math skills come in. So if I have a single bit, I can either be 0 or 1, right? It's got 2 possibilities. If I start multiplying those out, though, so I have 2 in this position, 2 in this position, 2 in this position, 2 in this position, I have a set of possibilities that I can have inside that byte. It's no different than when you're doing decimal. So if I write a number like 111 in decimal, what is that really? You remember that in grade school? You had to break that out where it was 100 plus 10 plus 1. Remember how you had to break that out? It's the same way in binary. All of these have a placeholder. The easiest way we can think about this, though, is if I can multiply by 2. So I want to know how many possibilities there are for this byte. How many different things can I count to? So what's 2 times 2? Times 2 again. Times 2 again. Times 2 again. 32. Again, 64. 128. One more with me. 256. You're going to see some of these numbers come up a lot. So there is the possibility of 256 different values in there in one byte. And what it really says is I can have the value between 0 and 255. That's 256 positions, 0 through 255. And those numbers are going to come up a lot when we start talking about IP addresses, when we start talking about game consoles, when we start looking at how our computer works. So this is big enough. If I have between 0 and 255, so I have 256 different chunks, I can start storing some data in there. I can store numbers, I can store letters, and what we generally refer to this is I can store one letter in each byte. So we've got something called ASCII, and you may have seen this before, where we have a chart that lists a decimal value between 0 and 255, and it lists a set of alphabetical values. So A, B, C, D, E, and in fact it lists the alphabet twice. Why would it list the alphabet twice? Why would it list it twice in there? Do we have different values for capital and lowercase? So I can use this then to start to convert into numbers and to letters and all different kinds of things. So these are really important sizes you're going to see. Now, because this is much bigger than that, when you get your internet service, they're going to tell you it's really, really fast, and they're going to tell it to you in bits per second that you're going to get, right? So they're going to say you can get all these zeros and ones. We know that the smallest chunk we can really use is 8 of them put together, but it sounds better to tell you it's 8 times faster than it really is, isn't it? So the computer thinks in terms of these zeros and ones. We can put these together into a byte. Well, we have one more number system we need to worry about included in here. So we know we can do zeros and ones. That's binary. There is another system. So when I passed that around and you guys all saw that MAC address looked kind of weird. Did you notice it had letters in it also? Oh, you guys are all going, right. So there is another system that we can use called hexadecimal. Or a lot of times we just call it hex. And the computer has a hard time calculating values in decimal. There's really some issues where we convert from decimal to binary, but to make that address, instead of being super, super long, we start doing it in hexadecimal. And that's called base 16. Or hexadecimal. And we have a problem. In binary, we have 0 and 1. We got those numbers. In decimal, we have what numbers do we have? 0 through, what's the biggest number in a single? 0 through 9, which gives us 10 numbers, right? 0 through 9, 10 separate numbers. Base 16 says, hey, there should be 16 values. So base 16 is 0 through 9 plus A, B, C, D, E, F. So there's actually 16 values. Well, here's where they kind of come together. We generally put, here we put 8 together to form a byte. When we write out hexadecimal, we generally write 2 numbers. So how many possibilities are there? 0 through 9 plus 6, right? So 10 plus 6 is 16. So each spot has 16 possibilities. What's 16 times 16? Does anybody know that off the top of your head? Oh. Huh. What do you think it might be? Oh. It actually turns out, remember that 0 through 255, that 256 up here? It's the same thing, because that's really 2 to the 4th. Well, we're not going to get into the whole, but that's 256 also. So rather than writing down 8 zeros and ones, I can write down 2 numbers here in hexadecimal. And so when you see those zeros, and then you see A, B, E, D, what that is base 16. And luckily, I'm going to show you the shortcut way to be able to convert those back and forth. But all of these are based on that idea of base powers of 2. So when I said those ports, there's 65,536. That's a power of 2. So those ports can range in value from 0 to 65,535. So if you can multiply by 2, you can get there eventually. And you can keep track of those and see how many sets of 2s I had to get to do that. And that also tells us a lot of other things. When you see something that says, hey, I bought a new gaming machine. So there's a new Nintendo Switch coming out in September. Has anybody seen that? Yeah. Great. I finally broke down and bought the Switch. Now a new one's coming out in a month. So the games you will see will say, hey, this is a 64-bit game. And if you remember back many years ago, there were things like Nintendo 16s, right? Way back in the olden days. That meant how many bits, how many of these zeros and ones it could transmit at one time, how big the bus width is. So we see this all around us all the time. So we have to figure out how we're going to send that data and convert it from, hello, Mom, I need money for food, send money, here's your email. So from those letters, all the way down to that zeros and ones that our computer can send. That's what we're really working with this OSI reference model. That model, so where we take this data, we're taking those zeros and ones. So we've taken those bytes that have that letter that say, hey, Mom, I need you to send money. We've converted that into, that's our payload. And now we've broken it into segments and we added some overhead. We converted that into then a packet and added some more overhead. And then we converted that to a frame to get it ready to send out. And that's all zeros and ones. That's the only thing our computers can send. They're not very bright, quite frankly. And we have to send a lot of them. And so this is that mechanism we are doing to send that. We're going to work a lot on these things of that OSI. We're going to look at what specifically we're sending and all those pieces. And we can look at some of those packets when we look at things like Wireshark. But I want to go over this a couple times just so you see where we're at and what's happening. So that those models where we're showing that overhead. So the other piece there is every time we send anything, here's our original payload. And this is certainly not to scale, but there are times when there's really more pieces, or metadata we call it, than there is actual data. So imagine you sent an email to your mom that all it said was no. By the time you actually send that, you're sending more metadata by the time you get those headers and those trailers and that information you actually sent. So these layers, this is the whole idea of the internet. So anytime you hear the word, hey, I need to fix the stack. If you're on NCIS or some of these computer shows, or if you're watching any TV, and they'll start talking about these things, that's how this works. We're just adding in those pieces. So we add in, how can I get to my own computer? How can I get to a computer on the local network? How can I get it anywhere in the world? So we're adding additional information about your computer and your pieces. So, this first chapter we talk about a lot of different things. So that OSI model is probably the roughest thing, quite frankly, to kind of start visualizing, but we're going to work with it a lot, and it'll become secondhand pretty quickly. But it's a lot of information, so I wanted to go through that and give you my take really quickly. Read the book. There's a couple of videos in there about it, and then there's actually an assignment that makes you look at that reference model from an application standpoint of how do I use that to troubleshoot. So I can even use that troubleshooting to see where an area is at. So let's do a couple of things that seem maybe less intimidating. So let's talk about what other things we need to know in here. So think about fires. Does anybody in here like to start fires for fun? Whoa, you guys scare me. I saw some hands going up. Wait a minute. All right, so let's talk about just some common sense, basic networking pieces when you're in somewhere. So, do electronics tend to catch on fire? Can that happen? Yeah. A lot of times when we have a data closet, we have a huge amount of power going in there. It can be an issue. So if I'm going to work in somewhere, one of the things I might want to know is, how do I get out? What's the best way to get out of this building? Door outside down. And we have fire drills occasionally, but have we screwed up even on our fire drills here? So many years ago, it's one of my first years here, and I vividly remember this. We had a fire drill. Well, the alarm goes off. We're just kind of sitting there going, what's this? I don't see any fire. Probably should run away. But, so we all went outside and we all met out in the quad. And so part of that is, maybe we should all know who's in class. All right. Ah, crud, we left somebody behind. What it turns out, though, we left an entire group on this campus behind in this building. So what's in the basement on the north side of the basement? Has anybody been in the basement? Daycare. Guess who we forgot to evacuate on our drills? Whoops. Great. I can only see the headlines. That would be bad. So we want to be aware of those kinds of things, especially in a building. If we had a data center, you have a lot of power, a lot of issues. So you might want to be aware of those things. Do we have a way to turn on a fire system? So in this room, if a computer catches on fire, do we have a fire extinguisher? Oh, and it's right over there by the door. So, you might yell at me, hey, and you run out the door, use the fire extinguisher. Now, I don't know when that fire extinguisher was last checked. I hope it was good. Do we need a specific type of fire extinguisher for electrical fires? Are there different types of fire extinguishers? Yeah. And in fact, in a closet or a data center, we may want to do something else. Do we want to turn on the sprinklers and dump thousands of gallons of water into a highly electrically charged environment? Does that seem like a good idea? No. So there are some other things we can do for fire that just put out the fire. Now the problem with those is, to get rid of the fire, we either take away the heat with water or we take away the oxygen. Okay, got it. If we take away the oxygen, that's another problem. What's the problem with taking away the oxygen? If you're in there, yeah. So you want to be aware of what's going on. Most people, though, we have our little data closet here. Do you think we have anything in there for a fire suppression system? No. We do actually have a sprinkler system that'll dump water on it, so that would be entertaining. Not in a good way. So you're going to see a lot of those things in there. So some of this is just common sense. when we're working back in the lab, there are electrical panels back in there. There is some electrical pieces. And so I want you to be aware that we don't do anything really dumb. I'm going to hand you guys cutters so that we can cut network cables and work on them. If you were to accidentally grab an electrical cable that's plugged in the wall and use that cutter, you're going to get the living daylights shocked out of you. So make sure that you're using the right tool, that you know what you're doing. I actually saw in a data closet not too long ago. So if you're not aware, there's basically two voltages in the United States. 110, 120, whatever it is, the low voltage, like you plug most stuff in. And then the 240, like you plug in your refrigerator or your range or bigger equipment like welders. Well, a lot of the equipment we're going to use in data centers actually runs on that 240. I watched a guy manage to plug in 110 equipment into a 240 bus. It took some effort for him to do that, and smoke started curling out of this rack of $10,000 a piece switches. So his day went very badly. Now, he didn't get hurt, thank goodness, physically. Now, I will say he had to go down and pee in a cup. That didn't go so well for him, because apparently he liked some product that is not legal in our state, is not available in here legally. And so not only did he pee in the cup, he went home that day and didn't come back. So this is a guy that we were paying, I think, $35 an hour on a job. That's a pretty big loss. All because it started with, because quite frankly, if you're not doing it at the job site, I don't care, but the job employer did, and he cooked about $100,000 worth of equipment. We had to file insurance claims, it got ugly, and we had some time delays because we were supposed to be up and running. Now suddenly that equipment's not there. So electrical can be a problem. Even in our own lab back here in the back, we have some equipment that is heavy. So most of you are young, strapping young students, right? Some of you are athletes. Strong, healthy. Don't get hurt. When we're in there, we've got a couple servers we're going to pull out and move around. One of them is about 250 pounds. It's got handles for 2 people, if not 4 people, to carry it. Use those. And so we want to make sure you don't get hurt. So just kind of that common sense items in there. So you're going to see some of those in your book. And then, you know what? We got to worry about electricity. So not only the electricity that's coming out of the wall, but there is a very, very hazardous thing to electronic equipment. When you walk across the room in the winter and you get zapped when you touch the door handle, that's amusing, right? And it's even better if you can do it to somebody else. Walk up and like zap them, right? No. If you do that to electronic equipment, especially when we have it apart and working on it, we have things like anti-static wrist guards. We will use anti-static chemicals. It can actually do a couple of things. If it doesn't wipe it out immediately, what sometimes you have is shortened equipment life. So the same way that if you get something hit with lightning near your house, oftentimes it doesn't die immediately, but it's kind of odd. A month later, every piece of electronic equipment in your house will die. So we have to be careful of static electricity, and we have actually had some equipment get destroyed in here. Remember I told you the tales of, hey, we need to do something better with high school students and college students building a computer? That was one of the things we ran into, was that electric static. So in a bigger environment, we also do some things in those data closets where at your house, your air conditioning and your heating system, they heat the air, they cool the air. In a data center, not only do we heat the air and we cool the air, but we maintain that humidity level. So you may spray almost like a water misting system inside of a data center so it maintains that proper atmosphere. And so there you see a static strap, and we have some of those back in the back when we're working on things. Wraps around your wrist, grounds you and that at the same electrical potential. That way you don't zap some of the parts in there. Now, if I'm handing around parts out here for us to just play with. So here, for example, is a motherboard, a CPU, and all these fun things. We're going to start with you. Be careful on the bottom of it. If you stab your hand on the bottom, it does have pokey bits. So it will stab you a little bit. If I hand one of those because I know it's dead, we're using it, that's different. You don't necessarily need to unground yourself for that. But that was a representative motherboard that we're passing around there. So one of the biggest things we want to do in this class is teach you the skills of troubleshooting. How do I troubleshoot something? So maybe you're not going to be the person that eventually solves the network routing issue or the computer is dead issue, but there's a lot of steps you can take that will give you the power to make that easier. And if you own the business, do you want to make those things cheaper? If you bring out a tech and he spends 4 hours, that's a lot more expensive than he comes out and spends 1 hour, right? Because you've already got some of those pointed out. And if your business is only shut down for 4 hours versus a couple of days, it's much cheaper. So that idea of breaking it into parts. So what do? Asking users, identifying if it's every computer or if it's one computer. That will point us to some different theories. So we have ways we can break those down. And so we're going to talk a lot about how we break and troubleshoot things down. So in a lot of cases, businesses will have kind of like a flow chart of, hey, if the internet's down on your computer, what do you do? Check with another user. Are they also down? And we can work our way up to see where that root cause is of where a problem is. So this chapter has a lot of information. Close this out. Close. We have a lot of pieces to do. We need to make sure that everybody is in the correct place with Cengage. So we've had some issues with people in Cengage already. So here's a couple of tips to make sure you're in the right spot. If I click on a link in this course and it asks me to sign into Cengage, you need to contact me immediately so we can get that resolved. I have to contact Cengage and I send them a list of all the people that are affected, and hopefully they can correct that. Our bookstore made the unfortunate error, and apparently we can't fix it because it's something in the system they're using. It wants you to click on links in their system. Don't do that. What you want to do to get into this class, and in fact almost any of the CMIS classes, is we have embedded it with Blackboard. You have to be able to click on a link here and go directly to Cengage. If you have used an email address other than your campus.peru email address, you need to email me and get a hold of me as soon as possible, because you are also not going to be linked in there. So one of the things I'm going to ask this week, well, I know everybody's going to do all the assignments, and that'll give me a little clue when I say, hey, you guys haven't done those assignments, and you say, yeah, I did the assignments in LabSim, and then I'll know that we need to figure out a way to mesh those together. There are a lot of assignments in here. Some of these are 4 points, some of them are not. So I would like to go through that really quickly. So obviously the reader, we have some previews. The very first thing that you're going to have that actually has points is going to be a little further down. Scroll more. Walk away. So are these lab simulations. So you will have 2 lab simulations this week that you should have done. Lab simulation 1-1, lab simulation 1-2. And you also have this thing called a lab. This is live virtual machine. The labs are simulated. They're a cartoon. You push X, it maybe works, right? This, you are connecting to real computers sitting somewhere in the internet. We don't know where. They're somewhere in Cengage's data center. These are virtual machines, and you are going to connect into them. The lab sims are pretty quick. these will usually take at least an hour to do those labs. And that one actually shows you some of the steps in troubleshooting using that OSI model. Before you do those, you need to do everything. This is in order. You need to do everything above them. So it really is in order. So there is a link down here. If you get down and you get stuck, this introduction to MindTap, but it also explains some of the other items. You need to do the quiz. The quiz is graded. It is 20 questions, and it is done within Cengage, not within Blackboard. Yep. So everything in here you should do in order. The lab simulations and the lab are graded. The quiz is graded. As we scroll down, we're going to actually start Chapter 2 on Wednesday. So, or Unit 2. You should go in here and do the reading. And there is one assignment due also out of Chapter 2. The quiz will actually be in week 3, so it will be due not this week, but the week after. So, there's a lot of reinforcement before you do the quiz. This would be a great thing to do. There's practices including those crossword puzzles for terminology. There is a lot of information in there. Finally, the last thing in here is a link to Facebook. I thought it might be interesting to see what companies are actually doing. Many of us use Facebook. They are actually building a data center in Sarpy County that is in excess of $1 billion. Probably would be a decent place to work. And so there is an article in here I would encourage you to read about how Facebook is doing IT. Now, they don't talk necessarily about everything. It's one quick article, but it shows you some of the things behind the scenes in Facebook. So, for example, they have self-checkouts for your laptop, so you can go grab it out of a locker. They talk about how they do repair work and different things. Facebook went from one computer to data centers around the world off of the idea of somebody who said, man, I wish I could connect with other college students, right? Huh. Don't you wish you would have had that idea? Yeah. And the ability to implement it? Correct. So, that is what we need to do this week. It looks like a lot. Work your way through. You should have already been doing quite a few of them. When I look through the grade book, I see that a lot of people have already done some of those lab simulations. I see a couple people, unfortunately, have done the lab itself, the virtual lab. The virtual lab, we're going to go over that again on Wednesday and take a look at it really quickly. It is a little more complicated because you're literally running another computer. And in fact, in some cases, you're running 5 or 6 or more computers remotely. All right. So I will try to record these as much as we can in class here for you. Do you think that'll be helpful? So I'm also going to make this available for the online students. So if you ask a question, I will try to reiterate it because I don't think anybody else is going to be able to hear it. So I'm not turned into your grandpa just repeating what you said, but I'm doing it so we can all be in together. All right, so the OSI model, it's tough. I wish I had a magic way to shove that into your brain. But we're going to see it over and over again. So practice it, work at it, pretend you're a message and see if you can make it through that almost like a game to get through there. There are a lot of reference pieces in here, so make sure you have done all of them. Here's the one thing I will say. I can see if you've done those. So if you come to me and go, man, I'm really confused. I said, well, have you done A, B, and C, and you haven't done those? I'm going to first point you to these. Say, here, do reference models A, B, and C. If you do that, it will hopefully help. So make sure you are working on these. It will take some time to do some of this. But this sets out foundation for how we can start understanding things later on. So when we start talking about wireless, or we talk about security and why this is an issue, it'll hopefully make a lot more sense. All right, any other questions? All right, let's bail. Remember,